Okay. So yesterday we were talking about branch prediction, and we also understood why branch prediction is necessary. Because we were just talking about simple 5-stage pipeline, but modern pipelines are like 9-stage, 11-stage, and right up to 20-stage. And depending on that, your uh, execution stage might be 5th stage or 7th stage or 11th stage. So to avoid that, and basically, if you are going to resolve your branch one way or the other in 11th stage, that means 10 stages you might be doing or executing instructions which were not to be executed because the loop was supposed to be taken. So that's why we thought that can we design a predictor which can sort of bring in a new way of predicting, or what should be the value of PC. I mean, if we do a good prediction, then the value of PC might be changed based on some kind of prediction algorithm that we have found out. So then we talked about two different types of predictors. We talked about static predictor, and then we talked about dynamic predictor. Now, in dynamic prediction, we talked about that we have I will not be doing predict always taken, predict always not taken. These are static branch prediction, and as I told you, they are used in ARM7 TDMI, and they more or less give you reasonably good results because most of the programs which are written on smaller processor, most of them have loops, and sometimes they have jump instructions or branch instructions which is going forward. So you make a very simple algorithm that backward branch predict taken always and forward always not taken. And more or less it would turn out to be correct because branches, as you might be taking 10 times before not taking it. So this is static branch prediction. Now we come to the dynamic branch prediction. In dynamic branch prediction, that means our hardware for branch predictor is trying to learn from the way a branch is being resolved. Now it is trying to think of two types of things. One is temporal correlation. That means a given branch, if it acted in a certain way, means if it went one particular way one time, the next time probably depends on that, it would be going that way too. So that is temporal correlation. And second is spatial correlation, means, if you've got three branches, 1, 2, and 3. So if branch number 1 and 2 resolve in certain direction, then branch number 3, based on that, would also be resolving in either the same direction or the different direction. So, and we can make these predictions based on these two properties. You may try to equate it with, what we did about memory. That, I mean, in memory, we have temporal locality of reference and spatial locality of reference. So very similarly in branch prediction, again, basically more or less it's the same thing. Here we are talking about a particular instruction in which way it is going to resolve. So there also we have temporal and spatial correlation. Then, we talked about 1-bit branch prediction buffer, and 1-bit branch prediction buffer is very simple. It would just flip between taken and not taken, and it would learn what the branch did last time. So I showed you this, that these are the number of loops which are taken: loop number 1, loop number 2, loop number 3, loop number 4. And in the first time, you start with initial prediction of not taken. We start with not taken because it's a convention. And if the actual outcome is taken, that means this prediction is wrong. So you go to the next time, you go and change it. So in 1-bit branch predictor, outcome of the last loop becomes the prediction for the loop when it comes again. So you say taken, and again, the actual outcome is taken, and think of a loop which is taken 100 times. So then, your prediction would be taken all the time, and, your outcome will also be taken all the time. So, you are going to get good result. And at the 100th time, it is also taken. But for 101st time, when you are supposed to exit the loop, your prediction would be taken based on the performance of the past loop, which was taken. But, then, it will be proved wrong. So basically, you are going to have two wrong results, right? So out of 100 times, you are going to be wrong twice. 101 times, you're going to be wrong twice. If I give you, this is 100 times, but if I say this loop is going to be repeated 1 lakh times, then first time and the last time if you are wrong, then your prediction accuracy is 99.99999%. So theoretically, you can always say that you are talking about almost 100% accuracy. Why? Because you are neglecting the first and the last one, because your sort of loops are like 1 lakh. So all the examples which I give, I will say this loop is executing 50,000 times, or 100,000 times, or 75,000 times. That means it is executing for such a large value that initial wrong result, which was there because of the way you choose your initial prediction, and the last one should not cause the result to wobble, right? Because here, if I had chosen initial condition is taken, then my prediction accuracy would have been 99%. If I choose initial thing is not taken, it changes to 98%, which is not right. So that's why in example I would give you a very large range, and then in the large range initial prediction, even if it is wrong, so if you are doing it 1 lakh times and you are correct 99,998 times, it is almost 100%, because 99.999 something is 100%. So we call this as 100% accurate. And you must remember this, and we are doing this just as to disregard small anomaly in the beginning and in the end. Is this clear to everyone? Okay. Now, we talked about branch history table. So let me, I did say something about branch history table. Let me expand it one more, because in examples which will be asked in the exam, it is very important that you understand what exactly we are talking about. So let's say I'm talking about branch history table. Or branch target buffer, so you call it BHT. So what we do here is, suppose I say I got 8 entry branch target buffer or branch history table, whichever you want to say. Now, just like cache, your branch history table should not be too big, because if it is too long, then you are going to have problem reading it, because someone asked a nice question that fetch stage has to do so much. Fetch stage first has to look at the branch history table or branch target buffer, and then go to a particular instruction, and then go and fetch that instruction, and sometimes it is available, sometimes it's a miss. So you can't have too big a branch history table. So you say I got 8 entry or 16 entry. So just like why first level cache has to be small, same reason is why your branch history table should not be too big. So we are talking about a toy example that, I got just 8 entry. So when I have 8 entry, how many bits would I require? I would require 3 bits. So my branch history table would have something like this, and it will end in 1, 1, 1. So it will be 0, 1, 2, 3, 4, 5, 6, 7. Now, this is basically has to be based on PC value. Now, PC value, as you know, program counter value is a 32-bit value, right? Because you are using 32-bit processor and your memory addresses are 32-bit. Now, how do you map this 32-bit into just 3 bits? So just like what we did in cache, same thing we are doing here. So the LSB of PC, we are putting as 000. And of course, we are neglecting the last 2 bits of your address because they are pertaining to byte, and we are talking about words. So we are going to use the values of 000, 001, and 111. Now again, just like in cache, we were having problem that many instruction or data from main memory could map onto the same location in a cache for a direct cache map thing. So here also, a lot of branches, if you have got a large program with large number of branches, then it may happen that some of the instructions map on the same line. And then you have this particular thing, say PC address, and then you want to say branch taken or not taken. So then you will have either taken here or not taken here. And if it is taken, then you also have to give target. Now here, if it is taken or not taken, so we will use T for taken and N for not taken. So do not misunderstand if I give an NT, this does not mean not taken. This means first it is not taken and second time it is taken. So this is, suppose if a branch is resolving like this. So for example, your loop, it would resolve something like this, that it is taken large number of times, and finally it is not taken, right? This is how your loop resolves. 100 time loop would be taken, and for the 100th time it will be not taken. So this will be a pattern. So for 000, it is taken. It may happen, and we are going to do this with an example, and I made you an example just a few minutes ago, and there is one very interesting example which would also prove a point that the size of the entry, size of the branch table, branch history table is also going to cause either a problem or no problem to you, depending on if there are like 2 branches which is resolving to the same last 3 bits. We'll talk about it a little later, but right now this is what we are going to do. Now, we have got 2-bit counter. Now, 2-bit counters are taken in a various ways. Usually, this is one way. This is basically a state table. I personally don't like this very much. This is not incorrect. Please remember that. This is, you can design state table anyway. The state table which I like to do and which is quite easy to understand is the one which I'm doing right now. So now, for 1-bit predictor, thing was pretty simple. So it is either taken or not taken, right? It is just one bit. So if it is 1, that means you take the branch. If it is 0, means don't take the branch, right? So there are only 2 states. But now if I have 2 bit, then I would have 4 states, right? 2 bits will give you 4 states like 0, 0, 0, 1, 1, 0, and 1, 1. So this is like not taken, not taken, not taken, 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 not taken, and taken and taken, right? So these are 4 possibilities. Now, how do you resolve this? And, because, you need to give a unique answer to the branch problem. You have to tell the program counter either you go to the next program count, next value, or you go and jump, at the beginning of the loop. So it wants either or answer. It does not want 4 possibilities. So we design a state table, something like this. So there are 4 states, right? As I told you, it is 0, 0, 0, 1, 1, 0, and 1, 1. Now, 0, 0, this you definitely say this meaning of this is not taken. And what's the meaning of this? What's the meaning of this? And what's the meaning of this? So 0, 0 you would say this is definitely not taken. And this is definitely taken. But what about this and this? So since we want the answer in just 2 possibilities, whether you take the branch or don't take the branch, we define this names as this, we call this one as strongly not taken and strongly taken. And this we'll call simply as taken. And this we'll call it as not taken. Now you may ask, what's the difference? What is a branch supposed to do if it gets the directive as strongly not taken, or it gets a directive as not taken? And we use only 2 things, either taken or not taken. So what does it mean? So in reality, not taken and strongly not taken both simply means N, means not taken. And strongly taken and just simply taken both means taken. Now you may ask, what good have you done? That, if you just wanted 2 states, then why are you wasting hardware, right? We will see why this is better than just 1-bit predictor. But before I give you an example, let me just teach you about the working of this 4 states. Now, when I give you 4 states, then as you would have learned in DND, that a transition is also required to be shown between states. That how can you go from this state to this state, or go from this state to this state or this state? So here I'm showing you the transition diagram. That if I'm in strongly not taken state, and this is my prediction, strongly not taken, and if the actual outcome is also not taken, then I would remain in this state. So this outside thing is the actual outcome. This is my prediction. My prediction is strongly not taken. And it so happens that the loop is actually not taken, when it was evaluated and came to execute stage, and, it was found out that it is in reality not taken. Then, we stay in this strongly not taken prediction state. But if my prediction was strongly not taken, but the actual outcome turns out to be taken, then I go to this state. Right? I transition to this not taken state. Well, now my prediction is not taken. If the actual outcome is again not taken, then I would move back to this state. So my prediction is not taken, actual outcome is also not taken. I transition back to this stage, which is strongly not taken. And now you can guess, if my prediction is not taken, but the actual outcome is taken, then I transition to this stage. I'm in this stage, which prediction is taken, but my actual outcome is not taken, then I transition back here. This is not taken. Okay. And finally, if I am in taken state and my actual outcome of the branch is also taken, means the branch is taken, then I move to this stage. So this is if my actual outcome is taken. If my prediction is taken, actual outcome is also taken, then I come to strongly taken stage. And now you can guess that if my prediction is strongly taken and if my outcome or the actual outcome is not taken, then I will go back to this stage. Yes, any question? If my actual outcome is not taken, then I come to this stage. And if I'm in strongly taken, my prediction is strongly taken, and if the actual outcome is also taken, then I remain into this state. Okay, it's a very simple thing. If you just get a hang of it, there is nothing very complicated. And does anyone want further explanation in this? Okay, so now let us take the same example which we took for 1-bit predictor. So now 2-bit predictor I'm using, and I'm again using a loop which is taken 99 times and not taken once. So basically this means exit condition, right? This is when you reach the exit condition of your loop. It is not taken, otherwise it is taken. So now, if you have, let's say, again, you have same transition table over here. It is not necessary that, you just call 1 as taken and 0 as not taken. You can do anything which you like, but, you have to define it. And this is general convention, so we stick to it because most of the people associate 1 with taken and 0 with not taken. But, you can change it. And this is my transition diagram that, this is basically strongly not taken, and if the actual outcome is also not taken, I just stay in this one. And if it is taken, then, my prediction is wrong. So I transition to this state. So let's study this problem. Once again, assume that, this loop, which I also used 1-bit predictor, now I'm using 2-bit predictor. So now in 2-bit predictor, I start off with this strongly not taken stage. And then, some of you again may ask, why start with this? Why not start with this or this? Well, that's a convention. You can change it in your design, but normally when people talk about initial condition, we think of initial condition as 0, 0. So we start as strongly not taken. So can you tell me how many times we'll be wrong for a 2-bit predictor?
Right?
In 1-bit predictor, you are wrong twice. Once while entering and second time while exiting. So what about here? How many times you will be wrong?
3 times.
Okay, and how?
2 times at the start and 1 at the exit.
Okay. So let us see. He said we'll be wrong 3 times, and let's see whether it is correct or not. So this is 0, 0 is strongly not taken. You entered the loop and the actual outcome was taken, right? So you were wrong once. You come here. Now, when you come here, what is your prediction? Again, it is not taken, right? But your actual outcome is taken. So again, you are proved wrong and you will be moving here. Now here, this is taken. I mean, the prediction is taken now and your actual outcome is also taken. So you will move here. I mean, you are correct, but you according to the convention, you are going to transition to this stage, which is strongly taken. Now, after this, you will be in this loop because your prediction is strongly taken and your actual outcome is also taken. So from, I believe it is the 97th time till you reach 0, you will be going around in a loop. So you were wrong twice in the beginning, as opposed to this, where you are wrong only once. And while exiting, you are strongly taken state. You are in strongly taken state. And if you are not correct, you will come here. So how many times you'll be wrong? Right? So 2-bit predictor will be wrong 3 times, as opposed to 1-bit predictor, which is wrong only 2 times. Now, this makes cause you to wonder that, then why should I use 2-bit predictor? First of all, 2-bit predictor is expensive. It is expensive in terms of hardware, right? You have to have 2 bits. So I mean, you have to have more space consideration. Also, there is a power consideration because, just to have the states and transitions, you require more power. And, even after spending more power and taking up more space and using more electronics, you are still getting wrong result. So, and, I still make an assertion that 2-bit predictor is quite popular as compared to other predictors. And can you guess why? I mean, even with this shortcoming, which I showed you, that 2-bit predictor is giving a worse off result simply because it is wrong twice in the beginning, as opposed to 1-bit predictor, which is wrong only once. So, why should I use this 2-bit predictor? Now, you may say that, okay, if I am using this loop for 50,000 times, then, again, this is of not much consequence. And again, my accuracy of 2-bit predictor is almost same as that of 1-bit predictor, which is 100%. But for a smaller loop, which is causing problem, say if I'm going to take a loop only 10 times, then, definitely my performance would be reduced. But, why would I still say that, use 2-bit predictor as opposed to 1? Any guess? Someone has said the probability of malfunctioning or error. No, that's not correct, because you can get malfunction in 1-bit as well as in 2-bit predictor. So let us assume that things are perfect.
Because hello.
Yeah, go ahead.
Because it doesn't change its belief like instantly. Like if one wrong, then they're going to predict taken in the next turn. But the 2-bit predictor doesn't do it.
Okay, so that is just its quality, or its characteristic. But how it is going to help you? I mean, initially I can see that characteristics is actually harmful. That if it were 1-bit predictor, it would have learned immediately. It would have immediately flipped from not taken to taken. Whereas here it took almost not almost, it took 2 tries to change from not taken to taken.
Sir, when we have another loop after completing one first loop, do this get reset or it stays where it is?
Okay, so let us take this example and try to understand this clearly. So when we finished this loop, we ended up in this state. And what is this state? This state is taken. Now, as I told you earlier, that most of the times you have loops within loop. Okay. So what would happen here is that, like, for example, matrix multiplication is a perfect example. That you have got a loop within a loop. So here, next time when you come to this particular example, you will be starting from this stage, because this counter would be stuck here for this particular branch, which is 1 0. So which says taken. So you start off from taken stage. So as soon as you enter, you are correct, right? And you are wrong only once when you exit. So you are here, and since the prediction was taken and actual outcome was also taken, so you will end up here. And then you will keep on going like this. And in the end, while exiting, you are wrong, you will end up over here. So for the first time, you will be wrong 3 times. Whereas in the second time, when you come to that loop, if it is a loop within a loop, then you will be wrong only once. And for all subsequent branches, you'll be wrong only once. Whereas for a 1-bit predictor, you'll be wrong twice all the time, whether you enter that loop for the first time or second time or third time. So that's why initially you get 3 wrong, but for subsequently, if that loop is encountered again and again, you will be wrong only once. Are you getting this argument?
Yes, sir. So, sir, this will only be improving the quality of
Say that again, please.
this. This thing will only improve the quality of prediction. So we prefer 2-bit.
Yes. Now you can also start with 3-bit prediction, and 3-bit prediction would be giving 8 states. So now you say strongly, and you will have to invent new names. So there will be for 8-bit predictor, there will be two more states over here somewhere, and 2 more states over here, and you will have to figure out the transition condition. So you will be wrong 4 times in the beginning, and then you will be coming out correct. But people have found out that 2-bit predictors are as good as n-bit predictor. That means more than 2. So if you want to come up with a scientific thing, or want to explain understand this more scientifically, you are taking example of an n-bit predictor. So that means counter can hold values between 0 to 2 raised to n minus 1, right? So for example, 2-bit predictor can hold values between 0 and 3 and predict taken when the value is greater than or equal to half of the maximum value, that is 2 raised to n minus 1. So if you want to understand this, for 2-bit predictor, I can have counter can hold values between 0 to 2 raised to 2 minus 1. So that means 3. And which values would give me a 0 value? So you say that, 2 raised to 2 minus 1. So that means 2 values would give me, say, not taken, and 2 values would be giving me taken. Similarly, if you have 3-bit, then 2 raised to 3 minus 1. So you have 0 to 7 states, out of which 4 states will give you taken, and 2 states will give you 4 states will give you taken, and 4 states will give you not taken. And you can go on, right? So then you can figure out the problem like this, but it does not have much benefit over 2-bit counter. So I mean, this is unnecessary amount of work, and you are trying to reduce power consumption as much as possible. You are trying to reduce electronics as much as possible. So 2-bit predictor is generally considered as okay thing to work with. Does anyone have any question? If we have 2 or more loops, so if you have 2 or more loops, see, when you say loop A and B, and then if you have loop C, which is embedded within it, is that what you are trying to say? Can the person who has asked this question can clarify it? Ashish, sorry, Vansh.
No, sir. I told for the previous 2-bit counter.
Okay. Right. Now, one must understand that, if I have a 2-bit predictor and, I'm writing a program, which is like, taking a loop only 3 times, then, you will say that, this loop will always give wrong answer. But, if you have just 3 repetitions, and if you want to write a program which is very fast, then, it is better to write inline program. So that means eliminate the loop, because loop is causing you problem, because of the loop you have to make prediction, or either you make prediction, or you don't make any prediction and pay the penalty. So it is better, I think, if you want to write a perfect program, then open up the loops, and you write the same procedure 3 times. So that means your program does not have to check any exit condition. It just has to do things 3 times. That's it. And this particular thing is actually used. It is known as inlining in your program. I don't know whether you understood this or have studied this or not. So what your compiler would do the same thing if you have not done it yourself. That compiler may try to open up the loop so that your processor does not have to waste time in checking the exit condition. But to do that, you have to make changes in the program, so that if you're writing an array in loop, it is very simple that in the end you say increment the loop and then go back. Whereas if you're writing it in line, then you have to manually increment the value in each one. It is not that just copy paste the same lines you have written for the first loop, you paste it again and again, one underneath the other, because then you'll be overwriting things. So there, you have to take care of those things. But, for small number of loops, it is always better to write a code which is in line, which is going straight and no checking condition. Loop should be written for like, 10, 20, 100, those kind of possibilities. Is this clear? Is this argument clear? Okay. Now, we are trying to come up with something. Before we end this, if you take the same example, which I gave last time, and last time I said, again, take example of a program which is or where the actual outcome of a branch is and it repeats. That means once you take the branch, once you don't take the branch, take the branch, don't take the branch, so on and so forth. So in 1-bit predictor, you will get 0% accuracy. Do you agree with me? Because first time, let us say you are right. Okay, because your initial condition is also not taken and the actual outcome is not taken. So you say, okay, this is correct. But from that point onwards, because you are correct, it would say the actual prediction for the next loop would be not taken and the outcome is taken. So you say, okay, for the next loop which comes, my prediction is that that loop will also be taken, but actual outcome is not taken, and so on and so forth. So for the large number of loops, you can say you will get 0% accuracy. Are you convinced with this argument? Or does anyone have any question? Okay, but suppose if I use 2-bit predictor, what would happen is I have 4 states again. And now I am not writing that, this is strongly not taken, and then this is not taken. Now probably you should remember it. So the first time my prediction is not taken and my actual outcome is not taken. So, I would remain here, but I will like to move from that point onwards. So my prediction is not taken. My actual outcome is taken. Right? So I come here. Now here again, even though my previous outcome was taken, my prediction still is not taken. Correct? Because this is not taken. This is strongly not taken. Okay. So I'll come here. And your actual outcome is also not taken, right? So you will come here. So you are correct second time. Third time, the prediction is not taken, but the outcome is taken. So you will come here. So you are wrong there. But here you are right. So what would happen is your outcome is actual. So let me again write for 2-bit predictor. Actual is not taken, not taken, taken. This is how the branch is actually resolving. And your prediction is not taken, not taken, not taken, not taken, not taken, not taken. So this is almost like a fixed thing that, backward branch not taken kind of prediction. So you're correct here, you're wrong here, you're correct here, you're wrong here, you're correct here. So you get 2-bit predictor will give you 50% accuracy. Are you getting these points? So 2-bit predictor in a corner case, which is really, really bad for 1-bit predictor, 2-bit predictor will give you 50% accuracy. I mean, it is not great, but it is not as bad as 1-bit predictor, which is giving you 0% accuracy. So now let us go with another way of prediction. Now, in fact, does anyone have any question? Okay. Yes, Kevin, you want to ask anything? Okay, so now I have got branch which is resolving like this. So actual resolution of branch is, say, taken, taken, not taken, 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 not taken, and it repeats. Let us assume that it is some kind of branch where my input is such that the outcome of the branch is taken first time, taken second time, but third time it is not taken, and so forth, so on and so forth. Now, I have to put this in my 2-bit predictor. So I will give you this as a homework thing. It is also asked in the lab exam that, for 1-bit. So someone says, if I use 1-bit predictor, what would be the accuracy percentage of, let's say, this particular kind of branch? So my 1-bit prediction, if I say no first time, I'll be wrong here. So this is actual, and underneath it, I should write prediction. Normally it should be other way around. So let me just do it that way, so that you can do this problem consistently. Okay, I think whatever I was doing, I've lost a little bit of data. But let's start from this pattern history prediction. My actual outcome is taken, taken, not taken, 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 not taken, and so on. I'm using 1-bit prediction. So in 1-bit prediction, Okay. Someone has asked a question that for the branch prediction, shall we write a program for it? So I don't understand the meaning of this thing. So you want to write a program which can figure out this branch prediction? Okay, probably Tarang asked this question. So if you can explain it to me.
Yes, sir. My question was that for this plant prediction, means do you have to implement this plant prediction in program, or will it automatically be implemented when we write the program?
Okay, so branch predictor is a hardware thing. So if you are a designer, if you are working on firmware, then you can design this pattern history prediction. So in fact, I will tell you later on that, there are many more sophisticated prediction algorithm and hardwares are there. So people who actually design it for the first time, they implement it in using C++, and they are doing a scenario thing. So yes, people do write a prediction thing, and then they test it on, say, benchmarking programs, and see the performance that which predictor is better. Sometimes they use multiple predictors, and then you check performance of each, and then they find out that predictor A is doing much better than predictors B and predictor C. It is giving consistently correct answer. They would increase the weightage of predictor A and reduce the weightage of predictor B and C, so that overall predictor A is the one which is giving you the answer. When all three of them starts bombing, then I told you the fall through mechanism, the word which was used as a fall through mechanism, which is used for forward branches, not taken, backward branches always taken kind of thing, is something which is known as a fall through mechanism, so that all your high end prediction mechanisms fail. Then you come down to this. So yes, initially people do write a program in C++, and when they are satisfied that a particular algorithm is working very well, then the hardware engineers come and they write an RTL code for it, and then they make it into a real thing. Okay, so I'm using 1-bit predictor. So the actual outcome, I'm just to avoiding the first one, which is not taken, because it is unnecessary. I will have to write one more loop. So I'm just assuming that the first one is correct. Prediction was taken. Actual outcome is taken. So now my new prediction is also taken. So this is correct. This is correct. Then my outcome is, actual outcome is not taken. So I'm wrong here. So my new prediction would be this one. Then, it will be wrong over here because actually it is taken. So I'm wrong. Then, I will be coming here, and, I will be correct over here. And again, the same thing would repeat. So this is one reason why I would like you guys to do this for at least 3 or more loops. Because, if you had stopped right at this one, then initial condition would have given you a wrong answer. I purposely started with taken as a first one, because if you just look at performance of this and give me the answer that this is correct 66% of the time, and it is wrong only once. So I mean, out of 3 times, 2 times it is correct and 1 time it is wrong. So accuracy percentage is 66%. Then you will go wrong, because what if I take this? Then I'm wrong twice and correct only once. So then you should do this certain number of times so that initial condition does not give you wrong result. Are you getting my point?
Yes, sir.
Okay. So whenever you are asked to do a pattern and design some kind of predictor that whether yes or no, then you should actually do it for at least 3 or more loops. So this is the first one, this is second, third. And if you're not satisfied, then go for the fourth, and then we'll get the actual pattern. If we just do it once and then initial condition would throw you in a wrong way. And suppose if you had done only this, then because of the initial condition which you used as taken, this is giving you 66% correct and 33% wrong, and which is not the right answer. Okay, so now 33% correct is not a good thing. Suppose if you just say that I'm correct only 33% of the time, then it's not a good prediction. I mean, you will say that I want a prediction to be correct at least more than 50% of the time. Otherwise, 33% correct result is nothing. So 2-bit predictor is actually no good. I mean, 1-bit predictor is actually no good. So now there is a new idea which says, previously, both in examples which we took, they were looking at only the previous outcome of the branch. So in 1-bit predictor, you would say, okay, the previous one was taken. So if the actual outcome of the previous branch was taken, so my new prediction is taken. If the actual outcome of the previous one was not taken, then I would immediately change my prediction to taken. So now they may say that there is no point of looking at just one previous output. You should look at like 2 previous ones of the same branch, right? So we are still talking about space. We are still talking about temporal correlation. That the way a branch resolves may be a good predictor, the way it will resolve the next time. But here we were taking only the last time what happened. Now you're saying, what about if we take about last 2 times, or last 3 times, or last 4 times? So you're talking about the same branch, but instead of saying what it did last time, we would say what it did last time and the time before that, or last time, time before that, and time before that. So we are looking either at last 2 times or last 3 times. So that is something what we call as pattern. So how do we assume that it is going to give us better result? So let's say this is how just one second. I don't know how can I make this go up? Okay, great. Okay, so now I'm looking for pattern history. So now what I will do is, we just do it in a new slide. Pattern detection. So now I would say the pattern detection, so instead of looking at what last time it was doing, I will look at it what it was doing last 2 times. And then I will make a prediction of taken or not taken. So let us say, again, I'm using the same branch, same program. And this particular branch X, it is resolving like T, not taken, 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 not taken, for infinite number of times. So now I would say that how many patterns I could detect here. So for a 2-bit pattern, I have to consider the resolution of 2 bits. So TT is 1, TN is second, and NT is third, right? There is no 4th pattern. There is no pattern like NN. So for 2-bit patterns, I can have patterns like TT, TN, NT, and NN. So here there are only 3. So I would say that if my pattern detection is a TT, then based on this, my prediction would be not taken. And how I have done it? By observation. Same thing like your hardware would do. If my pattern is, say, taken and not taken, then my actual outcome or my prediction should be taken based on this. And if I'm using something like NT, then my prediction should be T. Again, it is based on observation. Now, look at it. So this is your prediction bit, 1-bit predictor. This is your 1-bit predictor and this is pattern. So don't mistake between these two. This is 2-bit pattern. This is not 2-bit prediction. This is 2-bit pattern. And prediction is 1 bit, right? So either it is taken or not taken. It can't have any other value. So then, now look at this. You have got a branch which is going taken, taken, not taken, 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 not taken. And then, with 1-bit predictor directly applied on this, and considering the outcome or pattern of only one last time, that is 1 bit, it was giving me 33% result. But, if I use 2-bit history, then TT will give me N, TN will give me T, NT will give me T. And every time, this would repeat. And, I will not have any problem. So this would give me 100% accuracy. Do you agree with this? Any question?
Sir, can you please go to slide number 17?
Okay, so previous slide.
Yes.
Okay.
Here, sir, we started with taken, right?
Yes.
And sir, what is the prediction for third bit here?
See,
in 1-bit prediction, third bit, what is third?
We started off with prediction is taken, right?
Yes.
And actual outcome is taken, correct?
Yes, sir.
So now what would be the prediction for the next one?
Taken.
Yeah. And then actual outcome is also taken?
Yes. Then
So-
our prediction is taken.
Yes. So this
and-
is, just 1 second. So this is taken.
But actually it is not taken. So our next prediction is not taken.
Yeah, correct. So this is wrong, right? I mean, by mistake, I wrote T. Actually, it should be N.
Yes.
So this is not correct. So now we flip it to taken on
Yes,
based
sir.
on the actual outcome, right?
Yes, yes.
This was prediction was not taken. Actual outcome was taken. So next prediction is taken. And here it is T. So this is correct. And,
Yes.
And then, you will be wrong twice again.
Okay.
Yeah. Does anyone have any problem with this one? So,
Sir, again here in
yes, go ahead.
sir here again in TT after NT we will get the will we take the prediction as N again?
Yes, of course. See, so we have now divided up this patterns into 4 parts. There are 4 possibilities. So please do not confuse between 2-bit prediction. I mean 2-bit history and 2-bit prediction. This is 2-bit history where your previous branch and previous branch are taken, but the prediction bit is only 1. Okay. So then whenever the this thing this your prediction algorithm encounters taken and taken, that means the last time the branch was taken and the one before that was also taken, then the next one is not to be taken. So that it will learn. You may ask that, how it would do it. Then, this would definitely take some trials on the part of your program. But, the program is like loops are usually fairly large. So it would learn very quickly and stabilize. So if you start from very initial condition that, initial condition is nothing over here because it doesn't know. So TT, you would first write N, and then next time Tn is also not there, and then initial condition, you may give N, and then actually it is T. So I mean those things you will do. It will take give you answer would take some time to stabilize. But here I'm just cutting through the clutter and directly saying that after basically few initial steps of learning, it would gravitate to this. That the two previous time the branch was taken, and even before that it was taken, then the next time my prediction should be that it is not taken. How it is done? By actual experience or observation. Do you agree with this?
Hello, sir.
Yes.
Sir, is it like every possibility in 4-bit in a 2-bit history? It is a 1-bit predictor.
Yes. I mean, you can have 2-bit predictor also, right? Instead of this, but 2-bit predictor finally will give you one answer. So for changing states, you can have 2-bit predictor instead of 1-bit predictor. But 1-bit predictor is easier to understand that it would quickly change the value, whereas here it will not change the value. But you can as well have 2-bit predictor. So 2-bit branch history and 2-bit predictor you can have. I mean, there is nothing against it. And in fact, in real life things, there are 2-bit predictors and 2-bit branch history or more than that. But since there is just a few minutes left, and let me just explain, give you one more example. Like I like to give an example, where things are going to change. So I will give you an example where this particular example would bomb. So now I have a new pattern, which is taken, 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 not taken, 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 not taken. Now here, I want you to figure out what would happen. The patterns here are again TT, TN, and NT. But look at here. This TT, once the next state is T, and for this TT, the next outcome is N, right? So now, I want you to figure out that, what would be the accuracy percentage of this? Because if my branch is resolving like this, then, I have a problem that, right from 100% result, which I was getting on a branch, which was giving me outcome like this, the prediction accuracy was 100%. I'm very happy that, I've designed a great algorithm which can predict branch by 100% accuracy. But now, if I give you this, then, my pattern would be confused. That
it will be 50%, right?
Yes, I think I want you guys to figure out how much would it be. So there are 4 possibilities: TT, TN, NT. But TT is always going to give wrong result because TT is repeating twice. So for any set of things, twice you are wrong and twice you are correct. You are correct for TN and NT, but you're always wrong for TT and TT. I'm TT and dividing into 2 parts because it will be flipping. So, but I want you to do it methodically. And one last thing before we stop, someone has said use 3-bit predictor. Probably 3-bit predictor may give you a better answer, but that you need to figure out, because the problem which I have given you discusses things exactly like this. So we will discuss this problem in more detail on Monday. I have asked TAs to go through the problem which I sent you And quite a few of the problems which are given, some of the solution I've already given here. So, you know, it would be sort of a repetition for you. It would also teach you a concept of aliasing, where two branches are sitting on the same table in a branch history table, and then they are overwriting each other's result. And that is going to cause a disaster. So that also you will see in the problem which I have given to you. Any other question before we stop? Okay. So we are going to stop at this point, and we'll meet again.